On Friday, we were talking about the remaining chapters we have. So we have about three chapters left. One chapter is about stress transformation, one chapter is about yield criteria, and one chapter is about combined loading. So we talked about this on Friday. That I mean, we already have all the. If you want to calculate the stresses because of the individual loads, we have already done that in individual chapters. So in chapter three, we were talking about normal stresses because of the axial loads. In chapter 4 we were talking about torsion. We know how to calculate stresses when you have torsion. We know how to calculate stresses when you have shear force and bending moments, and also we know how to calculate the deformations for the individual cases. Now and also we just briefly touched pressure vessels. So if you have pressure, how you can calculate if you have hoop stresses and stuff. So now we're going to move to how we can combine those stresses, and if you have a bunch of different stresses combined, how are you going to deal with that. So in this we have three chapters left which are going to talk about these things roughly. So now we're going to combine all those loads, and then we'll try to figure out the combined effect of different kind of loads in terms of the different stresses we have already studied in different chapters. That's going to be in the combined loading part. And today we're gonna talk about stress transformations. We have talked about this on Friday, so I'm gonna just briefly overview that, and then we'll do some calculations. And this yield criteria chapter is about comparing those maximum stresses, combined maximum stresses, which you will get with the material property. So you have different methods to figure out either you're gonna have failure or not because of those combined stresses. So that's where we are now. So on Friday, we started this chapter 10, which is about stress transformations. So we already know that in case you have multiple external loads, you will have multiple internal loads, right? In chapter 3, we talked about normal stresses, we talked about torsion. In another chapter, we talked about shear forces and the bending moments. Because of these internal loads, you have stresses, right? So you can calculate individual stresses based on what type of internal load that is. So you will have a bunch of different stresses, and these stresses are also, we talked about on Friday, that they're not constant always. So for example, normal stress is, it's reasonably assumed that normal stress is going to be constant throughout the cross section, but that is not true with the shear stresses, with the axial stresses because of the bending moment. It is also not true because for the torsion stresses as well. So you can already see it's like a little bit of like you need to, it takes a little bit of work to figure out because normal stresses maybe are constant throughout, but torsion is different along the cross section, shear forces are different, bending moments are different along the cross section, also stresses are different. So if you have to figure out the combined effect of all the stresses, you need to do a little bit of work. So that's where we can get the maximum stresses. We're going to talk about this on the combined loading chapter, but this chapter is about stress transformation. And why this chapter is important, because once we get the combined effect, basically we can get the combined effect of all those stresses in terms of axial stresses and shear stresses, right? But the way we look, these axial stresses and shear stresses can be different based on our selected coordinate system. So if, so we need to do the stress transformation because we divide the combined effect of all those stresses in axial stresses and torsion stresses. But when you rotate the stress element, you're gonna have some of the axial forces may go to the shear stresses, some of the shear stresses may go into the axial stresses. So we have to figure out the maximum uh, of either of those and how we do this. So basically, we are trying to calculate the maximum stresses by considering all these. And the best way to do this is using Mohr circle. So in the very start of this subject, we talked about two approaches, right? We talked about the macro scale approach and we talked about the micro scale approach. So far, what we have been doing is a macro scale approach, right? We have an overall member, we cut a section, we expose internal loads, and we consider the entire cross section and we calculate stresses, right? But now we're going to see a micro scale approach because micro scale approach is much more efficient when we are dealing with the combined stresses. So, in micro scale approach, we just take out a very small stress element, and then we zoom in and we try to see what are the stresses acting on a stress element. So basically, on a very basic level, you have only two types of stresses. You have an axial stresses and you have a shear stresses. So axial stresses are of two type. In a two-dimensional stress element, you have stresses, axial stresses along x-axis, and then you have stresses along the y-axis. And then you also have shear stresses, which are parallel to the plane. So if you rotate the stress element, these stresses are going to change. Basically, overall stresses are going to remain the same, but it depends on how you look. So if you rotate the stress element, basically you are rotating the coordinate system. So some of these stresses will go there, some of these stresses will go there. So you have to figure out the maximum stresses, and those maximum stresses are going to cause failure. So that's what we have to keep in mind. So we have to first get the combined effect of all those stresses, and we're gonna put those stresses in these stresses, three stresses. So we're going to combine the axial stress along x-axis, we're going to put it here. We're going to combine all those stresses, we're going to put it here. And we're going to combine all the shear stresses at a given point, and we're going to put this here. Now we have to do the stress transformation. I mean, we have to do the rotation and see where we'll get the maximum stresses. And those maximum stresses are going to be responsible for the failure. So we talked about some of the advantages, why we are using microscale approach. Why don't we just consider the macro scale approach? So there are a bunch of different benefits. It is very efficient in handling combined loads, and you can visualize also when we draw Mohr circles. So you'll see we can visualize also the stresses. So in order to do the transformation, in order to calculate those updated stresses, when you do the rotation, we use which we call transformation equations. So there are three transformation equations for this, and these are those three transformation equations. So how it works is, so this is a stress element, right? And these loadings, this we got from the analysis which we were doing before. So we have a member, we have the loads, and we can calculate the combined effect of those loads in terms of stresses, which I have written in this stress element, which is stress x, stress y, and tau xy. Now, if you do the rotation at a particular angle, your stresses will change, right? So because if you do the transformation, you can calculate this, but you can also use these transformation equations. So these are the updated stresses. This is stress x prime, this is stress y prime, this is tau xy prime. These equations are written in uh, these are written in 10.1 force and stress transformation, but they use stress they have used the same symbol, but whenever there is a shear stress, I use tau instead of sigma, but it's the same equation. So stress x prime, which is the updated stress along the x-axis, transformed stress along the x-axis, is going to be the combination like average of stress x plus stress y by 2 and stress x minus stress y by 2 into cos 2 theta. This theta is the angle which we are doing the rotation. So these are the equations. You guys can write these down, and we will do one example. But the idea is that we have to figure out the maximum stresses, but we're going to start with just these equations, which are going to give you updated stresses uh, given some angle of rotation. So these are the equations. You guys can write these equations down, and we're going to do one example. So okay, so this is our problem. So we have a stress element and we already have a stress S for the stress element. This is 10.1. So this is our stress element. This is the stress along x-axis, which is 100 psi. This is the stress along y-axis, which is negative 250. So basically, the direction is going to be opposite. So this is a compressive stress. And then you have a shear stress, stress xy or tau xy, which is 100 psi. And where these values you're getting these values from the member. I mean, when you will be given a member with all the external loads, you will calculate the internal loads, you will calculate the stresses, and you will combine those stresses. And we're going to see how we can combine those stresses in the next chapter. But after you have combined all those stresses, this is what you will get. So you can extract the stress element from your problems. And once you have those stress elements, we just have to use the stress transformation to calculate the updated stresses. So in this question, what they are saying is that you have to rotate this stress element at an angle of 15 degree, and then you have to figure out what are going to be the transformed stresses. So you can use those stress equations. So these are the three stress equations which we have to use to convert these stresses into a transformed stresses given angle 15. So I can do one example in front of you guys. So our stress X in this case is 100 psi. Our stress Y is in this case is negative 250 psi. Negative would mean it's a compressive force. So it's already shown here. It is shown as a tensile force, but with a negative sign. So basically, it's a compressive force, but I will just put the negative sign in the figure just to show that it's a compressive force. And tau xy is 100 psi. So we all know the conventions. Tension is positive, compression is negative, right? But for torsion, for shear stress, it's positive when you have anti-clockwise rotation. So if you just look at this phase, this is the positive phase. So in this case, it's causing clockwise, so it's going to be negative. So this is what you have to remember basically. So if you see this phase, this is the positive x phase, right? And this force is gonna cause clockwise rotation, right? So it's gonna rotate the stress element like this. This force is pushing it down, so it's gonna cause the clockwise rotation. So that's why we're gonna put negative sign in this case, because clockwise is negative. That's a sign convention, yeah.
If you look at the top face, though, what's the opposite?
It would be opposite, but yeah, that's the sign convention. So we have to like settle with some convention. So that's the convention most of the books use, that because this is the positive phase of x-axis, and that's how this is also a positive phase for the y-axis, but that's how we see. That's the way to remember maybe.
So you go right side.
Yeah, yeah,
Okay.
yeah. So that's the positive phase of x-axis, that's the positive phase of y-axis, but we're gonna see the positive phase of x-axis and we're gonna decide if it's gonna rotate clockwise or anti-clockwise. Because essentially, this is basically the reactions for this. So this is the actual force, actual shear force. This is basically a reaction so that it doesn't, I mean, you have to equalize, right? So because of this, you are getting the reaction. So maybe you can, but that's a convention. So, you know, that's a convention. So we have to just see the positive x-axis and we have to see either this is going to rotate the stress element clockwise or anti-clockwise. So in this case, it's rotating clockwise. But there is no, I mean, logic behind it. It's like we have to select something positive, something negative. So we are just going with clockwise and negative.
Cool.
So now we can use the equation. This is equation 1, this is equation 2, this is equation 3. So stress x prime, updated stress would be equal to stress x is 100 plus stress y is negative 250 divided by 2 plus stress x is 100 negative stress y is negative 250 by 2 and then cos of 2 and you have degree was 15 degree, right? So we need to figure out the transform stresses if we rotate the stress element at a 15-degree angle. So we're going to use 15 degrees and plus stress is negative 100 and sine of 2 into 15 degree. So if you solve this, you guys can solve and try to see what you guys are getting. So 100 minus 250 by 2, this is negative 75, and then you have 100 plus 250 by 2 cos of 30 degree. So this is plus 151.55 and then negative 100 into sine 30 degree, it's gonna be 50. So you will end up getting minus 75 plus 151 minus 50. You're gonna end up getting 26.6 psi. So this is our updated stress X prime. So you can see that before our stress was 100 psi, now it has reduced to 26 psi. We can also calculate for stress Y prime, which is going to be this equation, and which is going to be 100 plus negative 250 by 2 and negative 100 minus 250 by 2 cos of 30 degree minus it's gonna be minus 100 sine of 30 degrees. And you can solve this. So you're asking about why this is why the stress is negative, this tau is negative.
Yeah.
Yeah. So it's a convention we have to select. So for the normal stress is obvious, right? Tension is we have assumed tension as positive and compression is negative. So whenever you have a compression force, you're gonna put negative, right? For the shear stress, the convention is that this is the x-axis and this is the x-axis face, right? So we have to see this face, which is along the x-axis positive, and we have to see this force. So basically, we have to see this force and we have to imagine either this force is gonna rotate the stress element clockwise or anti-clockwise. Or so this stress element is gonna rotate like this, right? So this is a clockwise rotation. So clockwise is negative. This is what we have assumed in the. So that's why we have put negative for the shear stress. So whenever it's a clockwise rotation of the stress element, you put negative sign. When you have an anti-clockwise rotation, you put positive sign. But you only have to see this force, the positive of x-axis. So if you do the calculations, you will get negative 176.6 psi. So if you guys are getting the same, So we can see before the stress Y was negative 250. So after transformation, it has reduced. So both the stresses have reduced. So basically, the stresses doesn't go anywhere. It's just like they went. So it's a combined effect is the same, but the normal stresses have reduced. So it's gonna go into the shear stresses. So shear stresses will increase and normal stresses will reduce. So that's why we have to do the rotation at like all the angles, and we have to see where we are getting the maximum. At some angle you're gonna get the maximum shear stresses, and at some angle you're gonna get the maximum uh, normal stresses. So those are the maximum stresses which we have to consider. So we can also calculate for the shear stress, and the formula for shear stress is it's negative stress x minus stress y. Stress x is 100 and negative 250 by 2 sine of 30 degrees plus negative 100 cos of 30 degrees. So if you solve this, you're gonna get negative 174.1 psi. So when you rotate the stress element at a 15 degree, these are the stresses you're gonna get. So you can see stress X and stress Y is like reduced. Stress X is reduced, stress Y is also reduced, and the shear stress is increased. But the overall stress would be the same. So originally this is what we had. So originally we had a stress along x-axis was 100, right? So originally we had stress x is equal to 100 psi, and we had stress y as 250 psi, but it was negative, right? So it is negative, so I'm going to just put the compressive sign. So it was a compressive force. Stress y was 250 psi, compressive force. And our stress xy was also negative, right? So negative means it's clockwise, so I'm gonna go this. So this is tau xy, which is 100 psi. And when you do the stress trans, so this was a coordinate axis, this is x, this is y. So if you do the rotation, so we want to do the rotation at 15 degrees, right? So if you do the rotation at 15 degrees, your this stress is reduced, and this stress is reduced to 26.6 psi, and the compressive stress is also reduced, and this transformed stress along y-axis at a 15 degree is 176.6 psi, and you have a stress also, which is negative. So I'm gonna do this clockwise rotation, and this tau xy prime updated is 174.1 psi. So if this is clear, I'm gonna write one example for you guys. So stress X in this case is, I'm gonna put, so stress X is 80 megapascals, and stress Y, I'll make it tension force. This is going to be 50 megapascals, and the tau XY is gonna be 25 megapascals. So what you guys can do is you can calculate at negative 30 degrees. So you can like use these equations, and you can try to calculate. So you can try to calculate the transformed stresses at an angle negative 30. So negative 30 would go down, right? So positive 15 was upward, so negative 30 is gonna go down. So the best way is first figure out which stress is positive, which stress is negative. So I'm gonna just write it down here. So stress X is compressive, right? So it's gonna be negative 80 megapascal, which you're gonna feed into the equations. This stress is in tension, so this is gonna be positive megapascals. And this stress is, this is the positive face of x-axis, and it's gonna cause clockwise rotation, right? So this is negative. Clockwise rotation is negative, negative 25 megapascals. And our 30 degrees also negative 30 degrees, right? So if you use the equation, this is what I am getting. So stress X prime I am getting is, oops, yeah, okay. So stress X prime I'm getting is negative 25.8 megapascals. Stress Y prime I'm getting is negative 4.15 megapascals. And tau XY I'm getting is negative 68.8 megapascals. So this is what I'm getting. Something like this. So our first stress is negative, right? So it's negative 25, so it's a compressive force, compressive stress. This is stress x prime is 25 mega, oops, 25.8 megapascals. So either I can just put negative and make it a tension stress, or make a compressive stress and use the positive sign. And this is also a compressive force, but it's a very small force. Stress y prime is 4.15 megapascals. And this is also negative, right? So negative would mean clockwise rotation. So our tau xy prime would be 68.8 megapascal. So we got